Okay, good morning. So let's continue with the lecture on tensor networks. So yesterday I got complaints that there were not enough formulas on the blackboard. So today I will not speak and only write formulas. So what was the point of the exercise yesterday is to convince you that the ground state physics is completely or even phase transitions are completely driven by the local correlations. Okay? By having to approximate local expectation values, because if your Hamiltonian only contains local terms, well, the ground state is by definition the one that has the strongest local correlations. So if you want to get a good wave function or a good ansatz, or to get an idea of the structure of the wave functions that that give rise to these ground states, you should only kind of care indeed about wave functions that are able to reproduce very strong local correlations. So this sounds a bit contradictory to the usual way in which you learn about condensed matter physics and statistical physics, that the long range properties are the relevant ones. But you have to keep in mind that all the long range properties, or even the power law decay, the critical exponents, all these things are completely driven by the fact that you want to maximize your local correlations. And it just turns out that the states that have the strongest local correlations also exhibit power law decay at some points. Well, that's something that comes to it. So somehow even criticality, even the long range correlations, are a consequence of trying to maximize the local correlations. And the question is, how can we do something like that systematically? How can we build up wave functions that would exhibit that property? So this is a very, very strong property. You don't care about non-local correlations for the ground state, only about local ones. And an extremely strong consequence of this fact is that ground states of local quantum Hamiltonians, and local now I really mean local in space, seem to exhibit area laws. And of course there might be some counterexamples that you can construct by some very ingenious construction, but of course all these constructions that, or these cases where you don't satisfy area laws, and there's actually beautiful papers written on this, are probably not very stable under RG kind of flows. So if you kind of add some perturbations, you will break all these kind of things. So I don't want to be extremely rigorous here, but somehow for most ground states of local Hamiltonians, and certainly for local gapped Hamiltonians, so you have a local Hamiltonian that exhibits a gap, you expect an area law. So it is actually an interesting question what a gap means in a thing, but I will postpone this discussion until the next lecture, in which we will try to classify different phases of matter using tensor networks. So there it will be important to indeed come up with a clear notion. What does it mean to have a gap? Why are some phases kind of protected and why not? And how is this going on? This is actually something that was lots of new insights into this question were brought forward by the works of Matthew Hastings that you probably already heard some things about in the previous lectures, but I will also kind of touch upon this. But let's postpone this discussion till the next lecture. So anyway, it turns out that if you have a system, so for example you would have a two-dimensional lattice. Okay, so these are points, and you could kind of imagine that this is the Hubbard model or some spin system, or doesn't really matter what, and you look at part of this lattice. Okay, you trace out basically all the spins, and you look at the reduced density matrix of this particular part. It turns out that the entanglement entropy, and we will be much more precise later in this lecture what entanglement entropy, because there's many different ways in which you can measure this. There's many different Renyi entropies or Schmidt coefficients, but we'll turn out that the entropy of this reduced density matrix will satisfy something like an area law. So the entropy of rho A will basically be proportional to the boundary of A and not like the volume of A. Okay, and this means that in some sense all the entanglement is concentrated along the boundary of that block. And that's what so people call it an area law because this is actually something that comes from 3 dimensions, and then you have a volume and an area. But of course, this so that doesn't really make sense in 2 dimensions, 1D. But still, people call this area laws. But it means that all the entanglement is basically concentrated along the boundary, because that's the only way in which you could potentially get something that scales like the boundary of your system, independent of the size of this block. Okay, so somehow all the entanglement, all the entanglement should be concentrated along the edge of your system, and that's very intuitive, because indeed, compared with the previous lectures, if you have a local Hamiltonian, you're only interested in minimizing somehow. If you you want to maximize the correlations between these 2 spins in such a way that, of course, these correlations are the same as these ones, or these ones, and these ones. So you're not interested in entanglement between this spin and some spin deep in the bulk, because somehow that doesn't buy you any energy. Okay, so it turns out that indeed your entanglement entropy seems to scale like the boundary, and there are some exceptions. So if you have critical systems, especially in 1 dimension, instead of having something like in a 1-dimensional system, what an area law of course means is that this entanglement entropy at some point should scale, should kind of reach a value that is independent of the size of this block. Okay, because the area in this case is just these 2 points, so there's just the edge of this, it's just 2 points. So the entanglement entropy in this case should saturate. And for critical systems in 1D, actually, it does not really saturate. It goes for a critical system like the log of the block, of the length of the block, with some prefactors. Typically this is C/6, but we will see, we'll be more precise later. But nevertheless, even in these cases, even if you have a critical system with power law, the amount of entanglement you have is exponentially smaller than you could have for a generic random many-body wave function. If you would have a random wave function and calculate the entropy of a small block, this would scale like the size of the block. And so even for a critical system, if there's only scales like the log of the size of the block, so that means that there's exponentially less entanglement than in a random state. So it means that actually all ground states are very, very special. If you have like your Hilbert space, this is like this hugely dimensional space. If you would have n spin 1/2, this dimension of the Hilbert space would be 2 to the n. While all the ground states, in some sense, they must live on a very low dimensional manifold in this hugely dimensional space, and this will be exactly the manifold of states that satisfy an area law. We will be much more precise in a few minutes to characterize this, but somehow this is the idea. Somehow the ground states, because of their entanglement structure, the fact that you only want to minimize or maximize the local correlations, imply that they will satisfy something like an area law, and that means that there might be an efficient way of parameterizing this. So let me, just for the sake of to give you an idea of how these proofs work, there's actually a beautiful way of proving a completely generic area law for arbitrary quantum many-body systems at finite temperature. Okay, so this is actually a 2-line proof in which you can prove indeed that for any local Hamiltonian, so I have a Hamiltonian sum over alpha, let's call it O alpha, but all these operators are basically local. Okay, so you have, it doesn't matter in what dimension, let's say 1 dimension, 2 dimension, or 3 dimension, but they are spatially local operators. They're like something like a Heisenberg model or a Hubbard model. It doesn't really matter which model, but your Hamiltonian is a sum of local terms. And it's like a 2-line proof to show that the thermal state, the Gibbs state of this Hamiltonian satisfies an area law for the mutual information. So you have seen in previous lectures like measures for entanglement. No? So there's like mixed state entanglement is typically very hard, but in particular for these kind of many body systems, this entanglement entropy is nothing more than the von Neumann entropy of this reduced density matrices. So the natural generalization to a mixed state of the entanglement entropy is the mutual information. So if you have, let's do it in 1 dimension. Okay, so I have a block A, and everything outside is called B, then the mutual information of this A, B is this entropy of A plus the von Neumann entropy of B minus the entropy of AB. And you see that for a pure state, SAB is 0, because this is, of course, the von Neumann entropy of a pure state has to be 0. That means that the mutual information reduces to 2 times the entanglement entropy. Okay, so the mutual information is like, but the mutual information is something that you can also define for mixed states. Okay, and what you can do in a very easy way is prove that for any Hamiltonian that is local and at finite temperature, this mutual information will satisfy an area law. And that's a very kind of strong indication that indeed, well, any system, so that this doesn't mean, it doesn't matter whether it's critical or not, somehow it is always true. So how do you actually prove this? It's a very nice kind of, very simple trick. So what is the Gibbs state of a Hamiltonian? Well, you have a finite temperature, you write e to the minus beta h, ab. That's clearly the times trace of e to the minus beta h ab. That's your equilibrium density matrix, your Gibbs state corresponding to your Hamiltonian at finite temperature in equilibrium. And we would like to prove that this density matrix satisfies an area law for the mutual information independent of the size of the block. So and this actually will happen in any dimension. It doesn't matter whether it's 1 dimension, 2 dimension, 3 dimensions. You can do it in any dimensions. And there's a very simple way of proving this. So this is rho AB. But now from your stat-mech classes, you probably remember that a Gibbs state is by construction the one that minimizes the free energy. Okay, so if you minimize the trace of rho times h plus temperature times trace rho log rho, so this is nothing more than minus T times the entropy. This is somehow the free energy of h at temperature beta. So this is the energy of a certain density matrix minus the T times the temperature times the entropy. Well, this is by definition, so you have to minimize this over all possible states rho. This will give you the free energy. And the state that minimizes this expression is, you can easily do this by introducing some Lagrange constraints and doing some optimization. This is certainly something that you saw in your first classes of statistical mechanics. You will see that indeed this is exactly this state. So the Gibbs state is by construction the one that minimizes the free energy over all possible density matrices. So that means that if I take any other density matrix, it has to have, if you kind of evaluate that expression here on the right hand side for it, it has to be a larger value. So let's take one possible value. Let's take rho tilde is equal to rho A tensor rho B, where rho A and rho B are actually the reduced density matrices of the thermal state. Okay, so you have this thermal state, and we take now another trial state, rho tilde AB, which is nothing more than the tensor product of the two marginals of your full density matrix. Now actually I leave it as an exercise to prove that indeed if you, so you know that the free energy corresponding to this state, so if you kind of plug this into this expression, has to be larger than the free energy corresponding to this state. You will see that most of the terms will disappear, okay, because this Hamiltonian is acting on most of it on A, most of it on B, and also on some places this H is acting on the interface between AB. But the expectation value for rho AB for all terms of the Hamiltonian that only act in A or in B will exactly be the same for this thing as for this thing. So you'll see that indeed the only difference, the only way in which these terms will differ for the Gibbs state and for this state are exactly for the terms that live on the boundary. And therefore, if you subtract these two things from each other, what you will get here is indeed something that scales like the boundary, something that is proportional to delta A. And on the right hand side what you will get is the trace rho AB log rho AB minus trace rho A log rho A minus trace rho B log rho B, which is nothing more than the mutual information that is defined here. And I leave it as a simple exercise to show that indeed by plugging this in you can immediately prove that at any temperature the mutual information of this I, A, B will be smaller than a constant divided by the temperature times something that scales like the boundary of A. Okay, so this means that indeed for any thermal state you automatically have an area law And this is a completely generic proof. This holds for any local Hamiltonian. It doesn't matter whether it's critical or not. But you also see that indeed there is some complication for ground states. For ground states, this thing breaks down because then the temperature starts, when the temperature goes to zero, this thing kind of diverges and you don't really know how to deal with it. Nevertheless, it's possible to salvage part of this proof if you can make some extra assumptions, like the density of states above somehow the ground state is small, is kind of limited by some polynomial, and so further then it should be possible to salvage this proof. But nevertheless, this is kind of a simple way of understanding that indeed if you have equilibrium states, Gibbs states, and a Gibbs state becomes the ground state when beta goes to infinity, you satisfy something like an area law. Okay, so but let's try to be constructive now. So are there questions about this? Yes?
For pure state, SAB is 0, right?
No. Ah, yes, sure, SAB is 0.
Total, right?
So
then what do you...
So then this mutual information is 2 times the entanglement entropy.
Because they're equal together.
Yes. Yeah, sorry. SA is equal to, yeah, that's the thing. If you have a pure state, it doesn't matter whether you calculate the entanglement entropy. Actually, this is related to the fact that if I have a matrix that the spectrum of x dagger is equal to the spectrum of x dagger x. And this follows that row. SA is equal to SP.
But then it's not an area law, because SA and SP don't, you know.
No.
So I'm saying, like if you, like for one of these critical systems, you would get like a log L. Are you calling that an area law?
Yeah.
As opposed to a constant? I mean, I think of it.
Yeah, well, that's what I'm saying. So even if there's some even if you would have some logarithmic corrections here, I would still call this an area law because a log is still exponentially smaller than, well, that's something that is scaling a volume. And also for the constructive approach that I will kind of start now with tensor networks, you will see that indeed these logs don't really matter too much. It will still, so you will still be able to approximate ground states of gapless systems with polynomial effort. And it doesn't matter whether it's whether this logarithm is there or not, will not really affect the conclusions.
But somehow it's still, I don't know, maybe it's just semantic, but, well, it's not semantics. I mean, log is non-trivially...
No, sure, log is much larger than constant, sure. Yes, no, I agree, and it's an important distinction, and it's an extremely important, well, it's a cornerstone, of course, in the whole CFT, and I agree, it has lots of consequences, the fact that there's a log there, but for the things that I want to discuss, the fact that I have a log there or a constant will not really be that important, certainly not in 1D, but in higher dimensions actually this is indeed much more relevant.
But I guess I'm going to ask you, clarifying, what a clarification on maybe. For the thermal state, when you say it's less than a boundary term area law, you again mean with this caveat that it could be...
No, this is completely generic for any state, even if it's, but that's finite temperature.
Right, but so does this...
There's no lock possible here. No, this is not, because this term just comes from this trace row H minus trace row A tensor row BH. So this is much stronger, yes. But it's at finite temperature. Yes?
So if we were to not know the Hamiltonian or even the locality structure, but simply know that there is complete translation invariance, there's essentially a high degree of symmetry, would that be actually sufficient to get some bound on mutual information?
No, because you can take any random state and make it translation invariant by just applying the shift operator to it, no? So you take the state and you apply the shift and then another shift. And of course by construction at some point this will become translation invariant, but it will still be very random. So the translation invariance is not enough to have area laws. Yes?
So I just want to sort of make sure if instead of dealing with the canonical ensemble with the Gibbs state, you sort of deal with the microcanonical ensemble, and you say that it's actually, my system is actually in a pure state at some energy density that's equivalent to the the canonical ensemble with the temperature corresponding to that energy density, sort of like ETH, then would it still have the short range entanglement? Because
No. In that case, obviously, you will have not an area law at all anymore, because SA is basically the same as for the Gibbs state, but SAB is equal to 0. Okay, so for a Gibbs state, at finite temperature, these things all have volume laws, no? So you have an extensive entropy in a Gibbs state. This is the entropy, so it's extensive. So this scales like the volume, this scales like the volume, this scales like the volume, but somehow it's just the difference between these things that scales like the area. And in the case of you're probably thinking about a quench or something in which indeed your system in ETH is thermalized, but still they have a pure state. Well, SA and SB will kind of will be indeed volume laws, but SAB will be equal to 0. So in that case, this is, but this is a very interesting, indeed, discussion. No? So it turns out that there is some distinction between classical and quantum correlations. And if you talk about the Gibbs state, you don't care about the classical. So and you look at the mutual information, you don't care about the classical correlations. Okay. And in these ETH and these states, these pure states that actually whose marginals look exactly like Gibbs states, what in some sense happens is that you replace these classical correlations also with quantum correlations, and that's not a very useful. In some sense, these are useless correlations. Okay, these are things that you will never be able to make use of them for some teleportation or some or whatever. This entanglement this entanglement is completely hidden in the many body correlation functions, and it's indeed a difficult question to make a distinction between classical and quantum. What are classical correlations? What are quantum correlations? I guess that Fernando Brandao might have discussed things like that in his lectures, but this is certainly not completely settled. Okay, so let's, now that we know that ground states satisfy something like an area law, let's try to construct states that would be good candidates for ground states of such systems. So let's start with the Heisenberg Hamiltonian. Okay, some ij si times sj with nearest neighbors, or of course you can also write this as some xi, let's do it in one dimension, plus yi plus 1 plus zi plus 1 with the x, y, and z, the Pauli operators. So yesterday we already briefly talked about this. If you write down this as a matrix and you only have two spins, the ground state of this is clearly the singlet. Okay, so what you have is this is SU2 invariant, so the ground state is a singlet and the triplet has an energy, this has a gap for just two spins. So that means that if you want to construct a ground state of such a system, what you would like is that all nearest neighbor, so let's do it in one dimension, I have this one-dimensional system, I would like that the marginal of these two spins and actually also of these two spins, so I would like that all the marginals are as close to the singlet as possible. So, but that's obviously, I cannot have two singlets because of the monogamy of entanglement. So let's try to, so it's not easy. It's not an easy exercise. Okay, so you could say, well, maybe I can try to have a singlet here and a singlet here, and so further. So this would be a dimerized state, and indeed, if you add some perturbations to this or some other terms to this Hamiltonian, turns out that this is the exact ground state. But certainly for the Heisenberg, it is not, because you completely break the translation invariant. So you would like to have singlets like this, but you also would like to have singlets at the same time here. And so the question is, how can I do this? How can I construct wave functions that indeed have strong local correlations, but are translation invariant at the same time? And the really deep paper where they achieved something like this was the AKLT paper, Affleck, Kennedy, Leap, and Tazaki. It's actually they constructed some wave function, some one particular wave function, not for the spin 1/2 Heisenberg model, but it turns out for some modified spin 1 Heisenberg model with some extra terms, but it doesn't really matter what they are for the model. But they constructed, they came up with a very nice construction of wave function and translation invariant in terms of something that resonating Valence bond, or actually something that we will call tensor network. So this is the first instance of a tensor network that was obtained. So let me briefly sketch how you can construct systematically wave function or translation invariant and will have strong local correlations. So we know that in this case, of course I have very strong correlations between these ones, and I have no correlations whatsoever between these two guys, if this is the wave function. So this would mean I have a tensor product of singlets, a singlet, a singlet, and so further. But now their idea of Affleck, Kennedy, Leap, and Tazaki is to say, well, actually, why don't we start from such a collection of singlets, but interpret these not these underlying spins not as the physical spins, but as some underlying virtual spins. So they say, let's make up our physical spin by taking some linear combinations of these underlying states that I have here. So in terms of, I think the easiest analogy of this would be to think about a neutron. A neutron has like 3 quarks inside it. But you don't really access these so unless of course you kind of have very high energies, you never see that there's some underlying structure here. So what happens here is that you say my physical spin, so this is the degrees of freedom of my physical spin, actually consists out of 2 underlying lower kind of states. So my state, my physical spin is built up out of some underlying virtual spins, and it is obtained by just telling so what part of the Hilbert space of these 2 virtual spins corresponds to my physical one. And it turns out that this construction, if you kind of keep on doing this now, and you everywhere put the same linear map, okay, so this will be a linear map, so this will be, we call this tensor A alpha beta I, so this would be index I, this would be index alpha, index beta. So what you do is you start from a collection of singlets or of maximally entangled states. It doesn't really matter because all these things are independent of your basis in which you work anyway. So you start from a collection of very strongly correlated maximally entangled states, and then say my physical spins only have access to a subspace of these 2 virtual spins. So I have a tensor product here of 2 spins, and my physical spin can only see part of my Hilbert space. It's just like in a neutron, you have like a very large space there with these 3 quarks, but effectively you only have much less degrees of freedom that you can access if you kind of only have low energy probing. And this is exactly what is going on here. I have these 2 virtual spins here, but physically I can only access a subspace, and the subspace is given by this tensor AI alpha beta. So it tells you, look, this is nothing more than a collection. So this is, well, this is a tensor with 3 indices, and it's nothing more than a linear map that maps somehow the Hilbert space of this tensor product of 2 guys to your physical guys. So the number of degrees of freedom in this MPS, because this is actually already the most general form of a matrix product state, is actually the dimension of your physical Hilbert space times the dimensions of these virtual Hilbert spaces, but you have of course 2 of them, so you have to square them. So this is the number of parameters by which you can construct such a general state. So what is fantastic about this state is that it's translation invariant by construction, and it will also have very strong local correlations by construction, because you start from something that is extremely strongly correlated between these 2, strongly correlated between these 2. So if you, even after the projection, it's kind of clear that indeed the correlations between nearest neighbor will survive. And correlations between next nearest neighbor that were not there to start with will now emerge because of this projection. So the fact that actually this thing is now correlated to this will also make sure that this spin is now correlated to this, but much less than these 2. So that will give you rise to the decay of your correlations in your spin chain. Okay, and this is the way, or at least the way that I kind of try to like to understand these wave functions. So this is clear that these are indeed wave functions that satisfy these criteria that we wanted, that we laid out yesterday. So it will be translation invariant, it will have the symmetries of your system, it will have strong local correlations. So the question is, how good is this? How good is this of an ansatz? What can we do with this? And this construction is actually the construction of matrix product state. But before we start being a little bit more rigorous, let's you can immediately feel or see that indeed this construction can be done in any dimensions for any geometry. It doesn't really matter. So what would happen, for example, in 2 dimensions? Well, on a square lattice, you would start with a collection of maximally entangled states. You kind of construct. So the underlying idea is I have a certain Hamiltonian with some structure, with some locality, with some geometrical structure. And everywhere that I have a term in my Hamiltonian, I put a maximally entangled state between the 2 spins, or between the two physical spins that I want. So this will be one side here. And like if you have a square lattice, it would have, and only nearest neighbor interactions, you would have an interaction term here, 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 and here, while you put a singlet there, 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 and there. Okay, and you do the same thing for this one, and so further, and then there would be one physical index. Okay, and this would be a state AI, alpha, beta, gamma, delta. So this would be one tensor that describes basically this whole state, and it would again be translation invariant by construction. And well, again, the question is this a good ansatz? Is this indeed a reasonable way of understanding? So you understand, you just fill the whole square lattice with this. You can do this for any lattice, for any dimension. And these constructions are actually, these are indeed the most generic class of tensor networks that we will talk about in these lectures. One of the nice things also of these states is that they satisfy an area law by construction. So exactly because you have all these singlets and then you just project these things down to a lower dimensional Hilbert space, it's very easy to prove that, like these PEPs, actually these wave functions are projected entangled pair states for obvious reasons, because I start with maximally entangled states and then I project them down by these linear maps. All these states satisfy an area law by construction. Okay, so, and why is this? It really has to do with the rank. So if you kind of take a certain patch and you kind of calculate this entanglement entropy of this patch, you can actually calculate the rank of that local reduced density matrix, and this rank will scale like an exponential in the area, somehow in the boundary, the size of the boundary, but not in the volume. So all these states indeed have area laws, they have very strong local correlations, they have the symmetries, so they seem to be very good candidates for ground states of local Hamiltonians. Let's see. So
what about criticality? So how can we all if we fix the bound dimension?
yes. So indeed. So I didn't make this maybe entirely clear. So this is for a general d-dimensional. So the example I gave you was a 2-dimensional case, but then for a general case, you can just take here I equal to 1 to d I. Okay, and it's clear that if you calculate the entanglement entropy for this kind of state, you will always satisfy, or it will always be upper bounded by some function of d. Okay, so if d is finite, you will never get this logarithmic corrections to the entanglement entropy. So you will have to go to large d, but not very large d, obviously. It's clear that if d scales like a polynomial in the block size, you will get where you want. So what happens? What will happen if you want to describe critical systems with matrix product state with finite bond dimension is that it is like you introduce some tiny perturbation to your critical system. So how do people study critical systems? If you look at like the way that Cardi developed this whole formalism of finite size scaling or whatever, if you want to extract information out of a conformal field theory or of a critical system, you have to actually open up a gap and then look at how the gap scales with the system size. You have to either put it on a finite size, or you have to work at finite temperature, and then do the calculations there, and then extrapolate what happens if the temperature goes to 0, or if the system goes to infinity. But at the end, the calculations always have to be done at the finite size. what these matrix product states will allow you is to kind of have a new way of finite size scaling, namely finite entanglement scaling. But it's very similar in spirit to working at the finite temperature. So working with the finite bond dimension and approximating or simulating a critical system will be very much like adding a tiny gap to your system and then study how indeed all the properties as a function of this gap. And that's why actually it's perfectly possible. So in practice, critical systems, the best way of studying critical systems in 1D is actually also by these tensor networks. But you have, of course, to be careful. You will always have to do the scaling, just like in this whole formula of CMFT, you will have to do the right scaling as a function of the bond dimension.
How does it scale with the bond dimension?
Well, I will talk about this. Okay, so but the cost. So you will have to define exactly what it means. Now, how does it scale? What is it that you want to scale? But it's clear that because it's only logarithmic, the entangled entropy, that it will be enough that this D scales polynomially in the system size. And which means that you will indeed have, like even if for critical systems, you will have an exponential breakdown. So this exponential wall will break down to a polynomial wall, because the number of this bond dimension D will only have to scale polynomial in the system size, not exponential. So the number of variables needed to describe your system will only be polynomial, not exponential in the system size. So anyway, so once you have this construction or this construction in mind of having sharing some singlets or some maximally entangled states and projecting them down, it's clear, it's immediately obvious how to generalize this to any dimensions, and actually also to cases when you deal with fermions. Which is not completely obvious at first. So in one dimension, fermions are not really a big deal because you can always do a Jordan-Wigner. Although even there, you hide basically locality by doing Jordan-Wigner transformations. You go from something local to something non-local, or vice versa. But in the case of and if you look at it from this point of view, actually fermions are not a problem at all. So what you start is then from some maximally entangled modes in the fermionic, in the second quantization picture, and then just apply these maps there, and you do everything in terms of your second quantization or your modes to start with, and everything will kind of perfectly work out too. So it's a very useful way of looking at this, and we will come back to this later. So I don't have my quote here, but actually there's a beautiful quote of Feynman that anticipated this way of doing quantum many-body physics. So Feynman was very much concerned with, obviously, with quantum field theory and trying to understand how you could use the variational principle for quantum field theories, and he struggled a lot with this and never really came up with a solution, but then said that the reason that it's so hard, but also that there would be a way of kind of circumventing this, is by not having to simulate your full wave function itself, but just by having to have a way of approximating the local reduced density matrices. So what you want to have is some way of understanding what the influence is of all the spins very far away to your local degrees of freedom. And it turns out that indeed in such tensor network pictures, this is exactly what is going on. So if you kind of extend this to infinity, all the information about all these spins to the left of, let's say, these two spins is basically mediated by this kind of bond. Okay, so what you will have is you will be able to describe all the physics to the left of it by working on this virtual degrees of in this virtual space, because all the information about the left has to go via this bond. And this will give you a way of indeed understanding all the physics or the long-range physics or whatever you want, or by studying actually the physics on this virtual dimension instead of the physical dimension. So it's really implementing this this idea that Feynman originally had in a very explicit way. Okay, so let's try to be a little bit more precise now and try to understand how well these matrix product states can approximate ground states of local Hamiltonians. And for this, let's for the moment stick to the one-dimensional case. Okay, so spin chains. So, and again, spin chains you would think, oh, one dimension is not very interesting. That's actually not true. No, as we saw yesterday, the lower the dimension, the stronger the quantum effects. So indeed, in one dimension you have much more, quantum correlations are much more important in one dimension. They are still important in two dimensions and much less important in three dimensions. So so the one dimensional case is actually the most quantum case that you can have in some sense. Okay, so so let's consider a quantum spin chain. Okay, so I'm already kind of using implicitly here this tensor network construction, or this tensor description, where you would have indeed tensor sitting here, but it doesn't really matter. So if the bond dimension is infinity, anything can be written as a matrix product state. So let's for the moment look at an exact ground state of something like the Heisenberg model or any model that you're interested in. And indeed, let's split this system in two pieces. So this would be A and this would be B, and let's try to understand or getting some deeper insights into the entanglement entropy. Okay, so turns out that von Neumann entropy, like we discussed before, is not really kind of strong enough, or not so von Neumann entropy is not a measure by which you will be able to say that you can approximate a state with the matrix product state or not. It's not because you satisfy an area law for the von Neumann entropy that this implies that the matrix product state will kind of be you will be able to approximate it with the matrix product state. And this is because the von Neumann entropy is not sensitive enough to the tails of your distribution. So if you have like the reduced density matrix, and you look at the eigenvalues of the reduced density matrix, they will decay, obviously, because they have to sum up to 1. And to be able to approximate a state well with the matrix product state, you want that these Schmidt coefficients, or these eigenvalues of reduced density matrix, decay fast enough. And the von Neumann entropy is not really strong enough to be able to say that you will be able to do it well or not. So what you need is actually something that is a little bit more precise, which is a Rényi entropy. And I guess that you have seen this in your previous lecture. So a Rényi entropy is actually defined for a state rho. It's nothing more than 1 over 1 minus alpha times the trace of log of log of trace of rho to the alpha. So you have a state rho, you put it to the power alpha, you take the logarithm and you divide by 1 minus alpha. This is called the Rényi entropy. And when alpha is smaller, if alpha is equal to 1, you see that, well, this kind of diverges because the log of, you get the log of 1, so this is 0 divided by 0. You have to use L'Hopital's rule, and actually you get indeed the von Neumann entropy. So indeed, when alpha is equal to 1, the Rényi entropy is equal to the von Neumann entropy. But if alpha is smaller than 1, this thing becomes more and more sensitive to the tails of your distribution. Okay, because and if alpha is larger than 1, and this is exactly the case that people typically consider in quantum field theory, this Rényi entropies with alpha larger than 1, you're less and less sensitive to the tails of your distribution. So to be able to say that a ground state or a state can be well approximated by a matrix product state, it will turn out that a sufficient condition will be that a Rényi entropy for an alpha smaller than 1 satisfies an area law. Okay, for alpha equal to 1 is just not strong enough, but any alpha smaller than 1 will be good enough. And these Rényi entropies are a monotonically decreasing function as a function of alpha. So whenever you have an alpha, well, then all the alpha smaller than it are also, of course, okay. Turns out that if you calculate this this measure for quantum spin systems, and you have to make the distinction between two cases. So if they are gapped, then these things turn out to go to a constant. Okay, so you have some quantum spin chain or some Hamiltonian, and this Hamiltonian is gapped. Okay, so that means that the second lowest energy, or so the state that has the second lowest energy has an energy that is larger than a constant. The energy is separated from the ground state by a constant that does not go to 0 if the system size goes to infinity. That is basically the definition of having a gap. Well, if your system is gapped, then it turns out that its Rényi entropies go to a constant, which is perfectly okay. And if it's critical, and for this I mean it's really a translation invariant and it's like a CFT, then you can actually prove that this goes to C over 6 times 1 plus alpha, so 1 plus 1 over alpha times the log of the length of your system. Okay, so so even for a critical system, so it's not just a von Neumann entropy that satisfies this area law up to logarithmic correction. It's actually true for any Iranian entropy. And the only difference is that you have to add here the 1 plus 1 over alpha term. Okay, so this is multiplied by, you just have to multiply this entropy by 1 plus 1 over alpha. Probably this is this has to be 12 then to be consistent, because if alpha is equal to 1, this should really be the von Neumann entropy. It must be 6, and that is 3. Ah, okay, that's 3. Okay, okay. So, well, okay, I wrote it down here. So this is 3, and this is 6. Okay, so let's now see. So if I have a von Neumann or a Renyi entropy, yes?
Can you define matrix for us?
Yeah, but for the moment this is not relevant for the discussion. But I will. But this was the so a matrix product states are just all the states that you can construct like that.
Why are you saying that rate of decaying of eigenvalues should be high?
Yeah, I will explain this. This will follow now from what I'm saying. So. So let's see. So if I calculate my Renyi entropy for the full left of this thing, and it scales like, it doesn't matter, like a constant or logarithmically in the size of the block to the left, I would like to indeed relate this decay, or the fact that this is small, to the question how big does the bond dimension have to be of my matrix product state. And I will explain what this means, such that I would be able to capture the physics that is needed to get this. So for this, let's first introduce some measure, epsilon of d, which is nothing more than the sum over k is equal to d plus 1 to infinity of the lambda case. So what I have is my reduced density matrix. Okay, and this reduced density matrix has eigenvalues. And I define epsilon of d to be the sum of all the eigenvalues that starting from the d plus first eigenvalue. So it's basically the weight in the tail of my kind of distribution of eigenvalues of my reduced density matrix. Okay, so I call this the epsilon of d. Okay, and I'm interested in how fast this decays. Okay, and so for a given Renyi entropy, so and of course this d will of course be related to the bond dimension that I will want to do, because that's exactly how you will go from a completely arbitrary state to a matrix product state, will be by basically cutting at every link all the Schmidt coefficients that are smaller than a certain value, or somehow the Schmidt coefficients that are, well, the d plus first and all the larger, for all kind of the values of you want to cut all the small Schmidt coefficients and have an idea of how much of an approximation does that do, or how bad is this for my full state. So you start from a state in which you have lots and lots and lots of Schmidt coefficients actually exponentially match. And then you want to understand if I have some way of cutting away these Schmidt coefficients, and that's exactly what these matrix product states will do. How much weight or how much fidelity do I lose? Okay, and that's the kind of thing. So, and for doing this, you first have to have an idea of how fast do these Schmidt coefficients decay. And so for a given Renyi entropy, so let's ignore for a moment these formulas. For a given Renyi entropy, you can ask, okay, I have a distribution of eigenvalues. Okay, and I know that the Renyi entropy is given to S alpha. What is the worst case scenario? So what can I find an upper bound for the weight of all the small Schmidt coefficients, for the sum of all the small Schmidt coefficients starting from the d plus first one to all the other ones? And indeed, you can immediately see that by doing some very simple calculations, some elementary algebra, you can see that indeed this thing is always upper bounded, so you can prove that this is smaller than 1 minus alpha over alpha times S alpha of rho minus log of d over 1 minus alpha. Okay, this is some very elementary calculation. So for given a distribution of eigenvalues that satisfy whose Iranian entropy, this alpha Iranian entropy is given by S alpha of rho, what is the sum, what is the weight of the tail of this distribution? Okay, and you see that actually this has to decay, so because there's this kind of minus log of d, so you have an exponential here, a log of d, so you see that indeed this decays as a function of d, and it actually decays like a power law. Okay, now you can fill in these formulas for gapped or critical systems and try to see how these things have to scale, and you do this systematically. So there's several cases where you can consider this. So you could consider the case. So there's actually two cases in which lots and lots of calculations have been done, for which you know basically exactly what this epsilon of these is, or you find exactly upper bounds to it. So first of all, there's all these integral models. So there have been many papers where people have been calculating the Iranian entropies for integral models like the Heisenberg model, but many other spin chains are actually integrable. And for this, you know exactly what this formula epsilon of d is. It turns out that this epsilon of d, in this case, scales like exponential of minus c times a log of d squared. Okay, and why? How do you get this formula? It turns out that for integral models, your Schmidt coefficients are always decaying exponentially with somehow, well, there's some exponential law in which they decay, but the degeneracy of the different eigenvalues that are related by some exponential decay also grows exponentially. And nevertheless, the product of, if you kind of look at it, you combine these things, it turns out that the epsilon of d has indeed this this scaling as an exponential of minus c times a log d squared. So it means that indeed this decays very fast as a function of the bond dimension. So for the most generic non-integral systems, the work of Hastings, and then there were kind of beautiful papers that extended the work of Matthew Hastings, especially papers of Vidic, Lando, and Vazirani, and then also of a student Huang, who is now in Caltech, I think. So they proved that indeed this weight for any, if you have a gapped system, if you have a quantum spin chain with a certain gap, and you're interested in the weight of the tails of your distribution over one cut, then this epsilon of d is always upper bounded by, and I have to say some kind of like an exponential of minus a constant times the gap of the system to the power 1/3 to the log of the d to the 4/3. Okay, so these are actually exact bounds for any quantum spin chain in which the gap has been normalized by introducing some Lie-Robinson velocity. So you kind of normalize that such that the Lie-Robinson velocity is 1, then this gap is of course some kind of dimensionless quantity. Nevertheless, so this epsilon of d scales like this gap to the 1/3 times log of d to the 4/3. And it's important that this is larger, this power is larger than 1. So what it means is that actually these tails are decaying very fast. Okay, so as a function of d. So this is basically the weight of the Schmidt coefficients in the tail. It's decaying fast in the bond dimension. It turns out that this is exactly the reason, the fact that this decays fast, that matrix product states will be able to capture the physics of gapped quantum spin chains. And actually also for gapless systems, somehow bounds, these things decay fast enough such that you will still be able to capture everything that you want. So we know that the tails of this distribution are decaying fast. So let's now indeed look at the full exact state. So the exact state, the exact ground state, has a bond dimension here that would be exponential in the system size everywhere. Okay, because you can write any wave function actually like this. But now the whole idea of a matrix product state is to put projectors here that would project out. So in these bonds, so you can write any state as a matrix product state as long as the bond dimension is infinite. There's actually a triviality. You can start taking, you can take the first spin. It take a Schmidt decomposition of the first spin with all the rest. Then you have the second spin, well, take the Schmidt coefficient of these two with all the rest, and so further. You will see that indeed this bond dimension for any state increases exponentially with the system size. But you know, because of somehow these area laws, and especially these are much stronger than area laws, because they tell you something about the exact distribution of the eigenvalues, not just about the sum of all of them. So these are actually, these epsilon of these are much more precise way of defining what an area law is. If you put these projectors here, you can easily see that the error that you make by putting this projector, so if you have, so let's put these projectors here that cut out all the Schmidt coefficients smaller than a certain bond dimension, smaller than, or like all the Schmidt coefficients starting from d plus 1 to infinity. So you put these projectors here and you call this psi of d. Okay, and now you can ask, what is the overlap of the exact wave function with the wave function in which I put all these projectors there? Okay, such that I cut, such that there's a finite bond dimension at every one of these links. And you can show that this is actually larger. The fidelity is larger than 1 minus the sum over x epsilon x of d. It's not completely trivial to prove this. So what you do is basically say, okay, I had this cut and I know exactly all the decay of the Schmidt coefficients over this cut. And let me throw away all the Schmidt coefficients more than a certain value, but let's do the same thing here, the same thing here, the same thing here. So it's not completely obvious that because you already cut them away here, that this will not affect these ones, and so further. But by making use of the contractivity of completely positive maps and so further, there's actually some tricks that you can do, and I can certainly give you the references of how to do this. You can see that actually even if you cut them everywhere, the only thing that happens is that the error that you make is just the sum over all these weights that you cut away. Okay, so if you cut here and you cut there and you cut there and so further, well, at the end the complete fidelity of the full state with the one in which you cut everything away, and this would indeed give rise to a matrix product state with bond dimension d, would still be 1 minus the sum of all these kind of small values.
Doesn't that become negative for infinite length?
Well, this is yes, sure, but you have to, this is all in the limit when all these epsilons are very small. Okay, so you have to, the exact form, I agree, but even if it's negative, it's still this is still large, no? This is always larger than 1, larger than 0, so it doesn't really matter. The bound is still valid. The bound is obviously only relevant if all these things are small. And indeed, this will set exactly how big is the bond dimension. How big does the bond dimension have to be? Well, it has to be so big in such a way that this is still very small. Okay, so you want the fidelity to be larger than some previous preset number. You say, I want to have an overlap of my exact ground state wave function with a certain matrix product with a certain bond dimension. Well, this formula will now tell you, that's the bond dimension that you need. And indeed, if you work this out and you make use of these formulas that are written here, then the bond dimension that you will need for a certain epsilon, and this would be the full epsilon. You say, I want a certain fidelity epsilon. What is the bond dimension that I need to capture this? I have to see, well, actually this is, you can just fill in all these formulas. You will see that this is polynomial in 1 over epsilon and the length of your system. Okay, so that means that and again, this is an extremely strong requirement. No? So if the fidelity is larger than 1 minus epsilon, it means that any possible correlation function or any possible property that you can calculate of this state will be epsilon close to the original one. This is an extremely strong requirement to say that this fidelity is like this. And what you see is that the bond dimension, the number of variables that you need to achieve this, is just polynomial in 1 over epsilon and L, and the length of the number of spins in your system. And this is exactly what people mean that you break down the exponential wall with tensor networks. Okay, because you start from a wave function in exponentially large Hilbert space, where in principle you have exponentially many variables. If you want to specify a wave function there, you need exponentially many variables. Well, if you express it in terms of a matrix product state or a tensor network, you only need a polynomial number of parameters. Yes?
So how does this here work for the infinite case? Are you taking MRG or
Yeah, exactly. That's exactly what I wanted to say now. So obviously this breaks down is useless in the infinite case. Okay, but if you have an infinite system, fidelity does not make sense at all anymore, because there's this orthogonality catastrophe of Anderson. Two wave functions that are not equal and are kind of translation invariant have to have either fidelity 1 or 0. There's nothing in between. That's the orthogonality catastrophe. So if you have some symmetry like translation invariance and take two wave functions, well, either the overlap is 0 or 1, and there's nothing that is possible in between. And of course, it's just that the requirement is too strong. The fact that you want a fidelity larger than 1 minus epsilon in the thermodynamic limit doesn't make sense. That's not what you want. The real measure, or the real what you really want for a thermodynamic system and a system in a thermodynamic limit is that you can reproduce all the possible correlation functions, that you can actually reproduce the local reduced density matrices. So what you're interested is, I have a system in a thermodynamic limit, and I'm interested in approximating the reduced density matrices over small L spins. So I have like a contiguous block of L spins, and I want to know, and I have the exact ground state, and I want to know how large do I have to make the bond dimension such that this norm is smaller than epsilon. Okay, let's take the trace norm. Actually, you can work this out with exactly the same formulas, and this was first done by Huang. Actually, we didn't know that this was done, and last year, together with Norbert Schuch, we wrote a very small paper. It was always my dream to write kind of a paper of 1 page, and indeed we managed to do this in a 1-page paper. But after we had posted this paper on the archive, then Huang kind of sent us an email that actually our result was like in corollary 11.75 in his paper somewhere. Okay, but so and then we retracted our paper. But so this is at the end. This is the result that you really want. Okay, so indeed this is the strongest result that you want. To have an idea that in the thermodynamic limit, what is the bond dimension that I need, such as to reproduce the local reduced density matrices to a certain precision epsilon. And if you work this out, this d as a function of epsilon. So you say I fix an epsilon, and now I want to know how large I have to make d. Turns out to be equal to, or smaller than, this is an upper bound of course, 6 times L minus 1 divided by epsilon times the exponential of 2 times a constant times the gap. This is the same gap as this one, to the 1 over 4 now, and then the log L minus 1 times a constant divided by epsilon cube to the 3 over 4. Okay, so this is the bound. Okay, this might at first it looks a bit strange, but if you look at it more closely, because this is a 3 over 4 and this is an exponential, and when epsilon becomes small, okay, that means that this whole term here just goes to a constant, and the only thing that is relevant is this first prefactor. It turns out that the bond dimension just has to scale like 1 over epsilon. Okay, and linear in the block size. And this is at the end, indeed, this is the real deal. This is really what you wanted to see, that if I have a quantum spin chain in a thermodynamic limit, what is the bond dimension? What is the number of variables I need with my matrix proxy to approximate all possible local density matrices up to a certain precision? Well, basically this bond dimension has to scale like a constant times the length of the block divided by epsilon, and that's clearly kind of a polynomial kind of thing. So this is at the end I think this is the most relevant results. All of these results are of course very nice, but they are kind of trying to prove something that is too strong, and that's why the result is much weaker. But this is kind of the result that you want to prove. This is much stronger because this is about fidelities, but they don't work in a thermodynamic limit. But this is the result that you really want, and so this goes to a constant for small epsilon. Or this is actually much. Let's say this scales up. This is completely irrelevant. The scaling on epsilon for small epsilon in comparison to 1 over epsilon, and that's why effectively the scaling is L over epsilon, with L the size of the block.
What about legality?
Yeah, actually, yeah, you should indeed try to see what happens if this is so. Yeah, I don't know. I actually. For what I know is that for sure is that for critical systems, this is still valid. This is still exactly polynomial in 1 over epsilon and L, because there's nothing exponential. But for the case of a critical system, so it really will depend on how the gap scales even, no? Because there are systems for which there is no area law to start with, and then of course you will not be this will be very bad, this bound. But then indeed all these systems for which you have a violation of this area law, of this logarithm, even much stronger than a logarithmic violation, indeed this gap is extremely small, is much smaller than the gap that you get for a typical critical system, and that you would be able to fill this in, and so this bound is valid for any system with the gap delta. And then you fill this in, and indeed, if this kind of system, in the case of a critical system, this gap goes to 0, then again this bound doesn't really make sense. You will have to kind of put this on a finite size and see how the scaling is, and then you are kind of back to this case. But this case works. Okay, so this was a little bit to justify that indeed a matrix product state. So allow you to basically starting from an arbitrary state, as long as this state satisfies an area law, and an area law that is strong enough, namely it has to be an area law for the Iranian entropy, you will be able to approximate, you will be able to find a matrix product state with a finite bond dimension that has a very large overlap with it, or at least in the thermodynamic limit, for which the reduced density matrices are very similar. So let's so L would be, so I have my infinite system, and I say, okay, I'm interested in the reduced density matrix on L contiguous spins. Sorry? Well, there's no period, no? It's like infinite dimensional, but I say I want to approximate I want to make sure that my matrix product state is such that that the reduced density matrix of my matrix product state approximates the exact reduced density matrix of L spins up to an error epsilon. Okay, so and L is just, well, you can choose L whatever you want. No, it's like you want to approximate 2 spins or 3 spins or 4 spins. Well, and indeed it's L minus 1, because if you're only interested, for example, in approximating one, like the reduced density matrix of 1 spin, then of course the bond dimension just has to be 0. You can just take the tensor product of the local reduced density matrices. Okay, so let's know. So because this was, let's start to be more technical now, in the sense that let's try to get some feeling of how to deal with matrix product states, and how to calculate correlation functions. So what is the structure there? What are canonical forms, and things like that. Okay, so we have these matrix product states. We introduced them here in terms of these entangled pairs, but it's a very easy exercise to see that there's an equivalent description in terms of products of matrices. So these maps AI alpha beta, if you write down at the end your matrix product state psi, you can as well, you will see that, and let's actually for simplicity consider a system with open boundary conditions. I will have some boundary conditions, but let's ignore these boundary conditions for the moment. Times I1, I2. So I have n spins, and if you write down the explicit wave function that corresponds to this construction, namely this entangled pair construction, you will see that this is nothing more than a product of matrices. So AI, so as we said, this AI alpha beta are tensors with 3 indices. So if you specify index I, then this is a matrix with 2 indices. This is the left and the right. And if you write down the explicit wave function completely, you would indeed get the product of these matrices up to some boundary conditions. This would be a vector, a row vector. This would be a column vector. This is a product of matrices. Then here is the basis in which you write this down. Yes. Oh yeah. Indeed. You sum over all the i's. So it means that indeed, this is basically the wave function, like people in chemistry would call this the wave function. So in a translation invariant case, you would choose. So in a non-translation invariant case, you would put an extra index here. You would get different. These could be different tensors depending on where you are. So there's just. But in a translation invariant case, you either put, instead of left and right, you put a trace of a product, and this would basically describe a ring of spins, or you kind of go to the thermodynamic limit, and then these boundary conditions will kind of be defined self-consistently, as I will kind of show you in a moment. But one thing that is immediately clear and is important is that there is some redundancy in this description of matrix product states. Okay, because I have a product of matrices. So let's assume that all these A's are actually equal to each other. So so if I have an AI and I take an arbitrary matrix X, or let's call it G, AI G minus 1. So these two matrix product states will exactly correspond to exactly the same state. Of course, you have to choose your boundary. You have to adopt your boundary condition in the right way. But if you have matrices AI or G times AI, G minus 1, with G independent of I, and G is just an arbitrary D by D matrix that is full ranked, so that is invertible, these two matrix product state descriptions will give rise to exactly the same state. Okay, because what happens here is that I will have to introduce a G minus 1 here, but there will be a G there, and they kind of cancel each other. So there's some gauge degrees of freedom in the matrix product state description of, in this matrix product state description. And it will turn out, this for the moment just looks like a technicality, but it will turn out that this gauge degrees of freedom will be the key in understanding the classification of different topological phases of matter in 1D, but also in higher dimensions. So the fact that there is indeed some redundancy in this description will be extremely important in trying to distinguish different phases of matter. This is, if you have never seen this, this is not clear. This should not be clear at all by now, but for now. But we'll certainly kind of see this in the next lectures. Why this is very important. Turns out that these G's, we call them gauge degrees of freedom, and it's not a coincidence that we call them gauge degrees of freedom, because they are indeed related to somehow gauge. So you could, if you have a quantum spin system with certain symmetries, these G's will reflect these symmetries. You will be able to gauge those symmetries to get a gauge theory, and then you will lift basically these virtual degrees of freedom or some of these properties to the physical level, just like you kind of do with the minimal coupling procedure in quantum field theory, to kind of get from normal quantum fields to kind of gauge theories. And this is actually important. So the picture is, so I have my full Hilbert space. Okay, this is exponentially large, and I have here my parameter space. Okay, so this is parameter space. So this has like D times D squared degrees of freedom if I have a system that is translation invariant. So in this parameter space, there will somehow, this whole line and all these different points are related to each other by such gauge transformations. So any physical state in this manifold of matrix product states will correspond to a whole fiber. So actually this is, so to do this correctly and mathematically correctly, you have to describe this in terms of fiber bundles and all these things, but this is not kind of really important for us now. But it's important to know that many different parameterizations correspond to the same state in your physical Hilbert space. The very strong point that we have seen till now in 1D is that this manifold of matrix product states seems to capture all possible ground states, or all possible states that satisfy an area law. Okay, and if you have a gapped system, you know that you satisfy an area law. This has been proven. These are these results there of Hastings and company. So this means that indeed this manifold of matrix product states, as long as the bond dimension is large enough, seems to capture completely all the possible ground states. So this is a manifold of all the possible ground states of local Hamiltonians in 1D. And it's even vice versa. If you have a state on this manifold of matrix product states, you can actually construct a Hamiltonian, a local Hamiltonian, for which it is that is gapped and for which is the exact ground state. Okay, so it's in some sense it's a very strong statement. So in this one-dimensional, for one-dimensional gap systems, you have completely identified the manifold of all possible ground states. And that's very useful, of course, in practice, because typically it's very hard to find ground states, but you want to make statements about classification of phases of matter and all this. It's enough now to kind of make the statements about this manifold, and that's what we'll try to do later in these lectures. So, but let's first kind of try to understand how to, because of these gauge degrees of freedom, let's try to see whether there's a way of defining a canonical form for a matrix product state. Okay, so if you have your MPS, okay, so this would be kind of written in this form. Let's first try to calculate the norm of our state. Okay, just what is the norm? How do I normalize my state? So you take this matrix product state and actually put the conjugate on top of it. Okay, this is like you identify this spin. So this would be psi here, and this would be psi. And the overlap is obviously you kind of have to take the inner product within the i's. What you see is that indeed the overlap of a state with itself in terms of this quantity, so psi will nothing be more than pictorially this kind of thing to the power infinity. And let's assume that we have periodic boundary conditions, so it would be the trace. So I would have to identify this with this with this. So it will be the trace of this object here to the power infinity. Okay, so this is now a d squared by d squared matrix, because this is d-dimensional, this is d-dimensional. So this is a d squared by d squared matrix that I have to take the power of it to infinity if I'm working in a thermodynamic limit. And obviously, if I have a matrix and I put it to a very large power, the only relevant quantity is the largest eigenvalue. Okay, so I have a matrix and I turn it to the infinite power. Well, somehow the everything is exponentially decaying except the largest eigenvalue with respect to the largest eigenvalue. And obviously, for quantum physics, we want this the norm to be 1, which is indeed we want to normalize our matrix product states. We want to multiply these a's with a constant such that the largest eigenvalue of this matrix, because this is really, it's a matrix from these indices to these indices, this to the power infinity, you want this largest eigenvalue to be 1. So why is this always possible? It's actually a consequence of something that's called the quantum Perron-Frobenius. Okay, so probably most of you are familiar with Perron-Frobenius theory for stochastic systems. So if I have a stochastic matrix, then I'm guaranteed that the largest eigenvalue of that stochastic matrix is positive, that the eigenvector only contains positive elements, and there's some notion of ergodicity, that if your system is ergodic, then indeed its largest eigenvalue is unique. Actually, the whole Monte Carlo idea is based on this. The fact that indeed this exists, that the largest eigenvalue is positive, and so further. So the whole idea of Monte Carlo is based on this. Well, what we have here is some quantum version of this. So it turns out that you can understand the largest eigenvalue of this. This whole thing can be related to a completely positive map. So I'm not so sure that whether this has been introduced in the previous lectures, but turns out that the largest eigenvalue of such an object. So if you look at the left eigenvalue, so we would draw this as rho left times this is equal to lambda times rho left. So this would be the largest eigenvalue of the left of this object. This eigenvector, just like in the classical case for stochastic matrices, is guaranteed to be a positive matrix. Okay, so it's positive in the sense that the eigenvalues are all kind of positive. And if your system is ergodic, you're guaranteed even that this largest eigenvalue is unique, that there's only one of them with one largest value that's positive, and that rho left is full rank. Okay, so this is basically what follows from the theory of completely positive maps and quantum Baron-Frobenius theory. So of course you can also do the same thing from the right. You can look at the right eigenvector of that object. This will also be positive. The largest eigenvalue, of course, left eigenvalue is equal to the largest right eigenvalue. It's also positive. So you normalize that. Because this is positive, you can divide basically A by 1 over the square root of lambda, and then indeed for this renormalized MPS, this largest eigenvalue will exactly be 1. But anyway, so an important quantity is indeed the fact that this completely positive map corresponds to an ergodic thing, so that this largest eigenvalue is unique. And if it's unique, then we will call this matrix product state injective. Okay, and there's lots of results that depend on this notion of injectivity, but at the end, it just amounts to the fact that the largest eigenvalue of this completely positive map or of this matrix is unique, and that this fixed point is full rank. There's other kind of ways of understanding this, but for the moment this is enough. You had a question?
So even if it's not injective, this largest eigenvalue will be positive.
Well, then there will be several largest eigenvalues, and there's a guaranteed to be one that is positive, and the other ones will all lie on the unit circle. Indeed, this will be important. So we'll come back to this actually later. This one. But for the moment, this should be enough to. Okay, so now because we know that there exists just reduced density matrices that are positive, this immediately kind of gives rise to a natural canonical form. So a very natural canonical form would be to choose G to be equal to the square root of row left. So I have this AI, and now I multiply it from the left with row left, and from the right with row left minus 1. And I call this one AI in the left gauge. Okay, and why do I do this? Is because I know that for this AI left, if I draw this now like this, the left eigenvector will just be the identity. So let's assume that already we renormalize this such that the eigenvalue is 1. If I now choose a gauge transformation and this G is equal to the square root of row left, and I kind of redefine this matrix product state has to be the same as this one. But this one now has the property, obviously, that that I have to put the identity here, and that this left eigenvector is exactly the identity. So what it means is that in this left gauge, that this MPS is an isometry from these two indices to this index. Okay, because that's basically, I have an AI, I contract this index, these two indices. With an identity matrix, I get basically this thing is the pictorial way of describing the identity matrix. Okay, it has two indices. This index has to be identified to this one, so this is the identity matrix. So this would be the left canonical form of your MPS. Okay, so you can also choose G is equal to square root of row right minus, is this, yes indeed, square root of row right minus 1. And then you would indeed have that square root of row right minus 1 AI square root of row right is equal to AI right. And this is what people call the MPS in the right canonical form. Okay, so it means that this one MPS, so this might sound technical, but it's actually really relevant if you want to work with matrix product states, these kind of things. So what I have here now is that I have my MPS, my original MPS AI, and there's different ways of writing it in the canonical form. I can indeed write everything with AI left, but I can also kind of now decide that from here on I write AI right, AI right, AI right. But now if I do this, here I have to put an insertion, and this insertion would exactly be the square root of row left times the square root of row right. And it's a very easy exercise now to see that indeed if all of these things to the left of these insertions are in the left gauge, then these guys here, if you look at this set and you put an index alpha here for this thing, so then you would have indeed psi alpha left. It's very easy to see that all these guys or form an orthonormal set. Okay, because this is inherited from, this is automatically a consequence of this kind of gauge, or this property that the left eigenvectors have of that you're in the left gauge. So if you put an insertion here and you look at only A left guys, and you put this index alpha here as an alpha, and then you look at the Hilbert space spanned by all this of the spins kind of living on the Hilbert space to the left, these guys form all are all orthonormal. And the same thing for these guys to the right, they are also all orthonormal to each other with this other index. So that means that this matrix that is sitting here in the middle contains all the information about the entanglement of the system. So it turns out that the Schmidt coefficients, so if you write this as a singular value decomposition as a U sigma V dagger, you write, so these are row left and row right or D by D matrices. You write this now, okay, because row left, this is a D by D matrix because this is a D. This is really all this Perron Frobenius, but you write down the singular value decomposition. The Schmidt coefficients of this are exactly somehow the Schmidt coefficients that we were talking about here. Okay, so the eigenvalues of your reduced density matrix of everything to the left would be nothing more than the square of sigma. So the spectrum of row, let's say A, would be given by all these singular values squared. Okay, so these are the Schmidt coefficients of your system, and they are given indeed by the singular values of square root of row left times square root of row right. Yes?
So, the way to get to the canonical form, either left or right, can I just take it as, for example, you just write as a generic wave function, and you keep doing, iteratively doing singular Schmidt decomposition, and then you keep absorbing the diagonal part, either
Yes.
to the right.
Yes, that's
Right?
That's certainly, that would work. That's like a power method. In practice, of course, there's much better methods than that. Okay, we know that if you want to kind of do these kind of things, you don't want to do this with a power method. You want to do some Lang-Scholes type of things that give you quadratic speed up. But what you say would indeed work. And I didn't really plan to talk too much about algorithms and all this, but I can give you references in which you this is explained how to do this efficiently, because it turns out that indeed in any algorithm, if you actually want to use matrix product states in practice, it's extremely important to be able to calculate these things efficiently. I give you an MPS, calculate the left canonical, the right canonical, and in such a way that you never have to take inverses. Okay, so for the moment, this is not at all how you would do it in practice. In practice, you don't want to take inverses of this reduced density matrices, because the eigenvalues of these reduced density matrices, as we know, decay very fast. And therefore, if you take inverses here, they would be very badly conditioned. And indeed, so there's ways of calculating all these things without ever having to take inverses, which is of course exactly what you want. And this is, so let's see, so this is the left gauge, and there's also, another way of looking at this is now you can say, okay, let me kind of take this center side, okay, let's call this C, and let's absorb this C either with AR or to the left with A left, and then we call this AC. This would be the center side, and people that have ever kind of worked with DMRG know very well that this is exactly what you always use in DMRG. You use actually everything to the left, and you use a center side, which is basically a combination of these two, and then everything to the right. This center side is nothing more than A left times C, and it's also equal to C times A right. Okay, let's see. So maybe I can take you one more minute to, because I see it's time, but I started 5 minutes late. So, it's very simple what I want to do. I just want to kind of show you now how to calculate with an MPS expectation values. So once you have this canonical form, it's extremely easy to calculate expectation values for any observables. Okay, so I'll take an MPS like this, and let's say I want to calculate an observable that is living here on these two sides. Okay, so you have to put, this is the cat, and then you basically have to contract your whole thing like this. So what you do is, so the whole idea of making use of these canonical forms is to always, so it doesn't matter where you put a left and a right as long as you do it in a consistent way. So if you want to calculate such an expectation value, what you do is, well, I want to put everything here in the left gauge, also a left, and then I would put the center here and here in a right, and so further, and the same thing for the bra. Then this whole contraction, because we know that this is like infinity long, all these things will disappear here. And will give rise to the same thing here. And this will give rise to just an identity, and this would be a left bar, because it's a conjugate, a right bar. And now you have to contract just this local tensor network, and this gives you immediately the expectation value of this local operator. Same thing for structure factors. So there's quite a few or many apparently condensed matter people in the room. So for them, static structure factors or structure factors in general are very important. So this would be things like you take something like sum e to the I kx times an observable acting on x. You have your state psi and you want to calculate basically the norm of this. This would be the static structure factor corresponding to the observable OX. This is like an infinite sum with a certain momentum. You want to have the momentum dependence. Well, making use of such tricks with this a left, a right, it's actually completely obvious how to calculate this, and I leave this as an exercise how to do this. You will have to kind of come up with this at the end will kind of correspond to things like you have to put an identity here, then you have your a left, you will have your observable a left bar, then you will have to have 1 over 1 minus e to the I k times e, then you have an a right, your observable a right bar, and again the identity, and so forth. So what you will have to do is kind of basically do some conjugate gradient method to invert a certain thing, but all these things are actually pretty standard for matrix product state algorithms. So in these last minutes, what I wanted to say is that indeed once you have a matrix product state, there are many ways of writing down canonical forms for them. And using these canonical forms, it's very easy to extract all possible expectation values, and also to construct, for example, parent Hamiltonians for which these are the exact ground states. So I was able to cover much less than I wanted today. So I actually also wanted to explain how to go from this now to the picture of really taking this picture now seriously of the manifold of matrix product states. So what I have is this manifold in my full Hilbert space of all possible ground states or all possible low energy states of many body systems, and I want to do the physics now on this manifold. So this is the way in which somehow physics is always done. You have like an intractable system, so let's kind of indeed reduce the problem to something on a certain manifold and do the physics on that manifold. So this is also the way, for example, people that work with atomic physics and work with the Gross-Pitagoric equations. This is exactly how this is exactly what is done there. Now you start with the full Hilbert space as intractable. You kind of reduce the problem to a certain manifold of states in which you can work, and then do the physics on that manifold and describe the wave function or the evolution equations not in terms of your original Hilbert space, but in terms of your degrees of freedom that you have. So in terms of these AIs. So what you want to do is turn indeed your full quantum many-body problem into an effective problem or an effective physical problem in the space of your parameters, and this gives rise to nonlinear differential equations, and actually all of the physics, but also all of the algorithms that deal with tensor networks can be understood in terms of projecting your full evolution on this manifold and then doing somehow all the physics on this manifold. And this is what I wanted to cover today, but I didn't manage to do this. Thanks.